Hey gang, and welcome to another exam solutions walkthrough for the exam, Organic Chemistry 1, the final exam. Gang, if you are watching this video, just want to say, pat yourself on the back. Congrats, you've done a whole semester of organic chemistry, and while you're not done, right, and there's still work to do, there's something to say, there's something to be said about that. Good job, be proud of yourselves, but just know you have to bear down and just push through a little bit harder to get to that sweet Christmas or summer break that you're about to enjoy. Okay, so if you're here, you're looking for answers, right? You are looking, you've attempted the final exam that I've posted, you've looked at the answers, you want some explanations. Don't let me, keep you from them. Let's get after it and let's do this final exam. Okay, gang, to kick off this final exam, we have a slew of complete the reaction questions. This is actually part 1, so let's not waste any time jumping in. So, in this first problem, back to our roots. We have a methyl cyclohexane, but we have free radical bromination. We know bromine is picky, so the very first thing you're going to get kind of in an intermediate step is a bromine on that tertiary carbon. And then you can see we have our infamous big bulky base that is great for doing E2, but not only just E2, Hofmann eliminations specifically. So with this right here, you can see our least substituted double bond will be this tertiary primary elimination. So problem 1 looks a little something like this. Nice way to ease into the final exam with a Hofmann elimination. Okay, problem 2. So remember, we can clearly see we have double bond, we have HCl. This is screaming Markovnikov addition of HCl. So remember, mind your carbocations because they can shift. They are not planted, they move around quite easily. We have a secondary carbocation to start after the protonation of the double bond, right? But freeze, can we, relocate the carbocation? The answer is yes. We are going to do a methyl shift. So in doing that methyl shift, I'm going to use my space over here. We have this carbocation, then chlorine comes in and has no preference whether to attack above or below. So the product we get, and I will draw in blue, is in fact, I will draw chlorine as a wedge and that methyl group as a dash because we do produce a stereocenter. And what you can do, because we know there's stereocenters present, you can write plus an enantiomer because this will produce a racemic mixture. Okay? All right, on to problem 3. So you can see double bond. First step is treating it with MCPBA. So we produce an epoxide right off the bat. And what I'm going to do, I'm going to wedge my epoxide in my intermediate step. But again, remember, we will produce this epoxide as well as the dashed wedge version of that epoxide. So it doesn't matter which one you carry forward as long as you tack on a plus enantiomer at the end. And you can see we are in a basic environment. So remember, when we are in a basic environment attacking epoxides, it is a steric state of mind, okay? Fortunately, that didn't make Jay-Z's album, only New York State of Mind did. So, yeah, I had to thinking, do you tell a joke? Well, I did that anyways. Okay, so you attack the least sterically hindered carbon, right? There will be some work up at the end. So the product we get, you have your OH right there. That will come from workup, right? Because we're going to boot that right there. And then you're going to get a dashed OH right there, okay? And then, whoops, plus an enantiomer, right? Because we could have easily worked with the other epoxide, but we just chose to work with the one. Plus an enantiomer covers us, okay? So down here, we have an oxymercuration, demercuration, right? And we're just going to worry about regiochemistry here because of how the mechanism proceeds. Okay, so what we're going to do, we know this is a straight up Markovnikov addition with no shift. So we're going to stick an OH right there. Easy peasy breezy. On to the second part, problem 1. In the second part of problem 1, we have 4 more complete the reaction questions. So if we take a look up here, right, we have 4 steps on this first one. So I hope what you're seeing is a primary carbon with Cl, a tried and true good leaving group. And we have sodium hydroxide. So really all we're doing in the first part of this first reaction is doing a simple SN2 reaction. We don't even have to worry about stereochemistry. We're just swapping out the Cl with an OH. Then in step 2, we're going to oxidize that sucker with PCC, just going to the aldehyde. So I hope you're comfortable with me just kind of working off of this right here. This would be 2, so check, check. Now we attack with the Grignard and do workup, so it's almost kind of like one step, if you will. So what we're going to be doing is just kind of bringing in our Grignard, attacking, picking up electrons. So our final product will look a little something like this. So it's 1, 2, 3. Okay, good. I'm going to dot that carbon. This will be my OH, and that dot carbon will be attached directly to our methyl. I have the workup, with the H already there. That is that first reaction. Now, down here, I hope what you're seeing is we have an alkene, and we have conditions for ozonolysis. So I'm going to kind of lump these right here, and we're going to be making aldehydes and ketones. So what I'm going to do is I'm going to go ahead and number my ring 1, 2, 3, 4, 5, and 6, because we are going to get some molecular scissors out, and we are going to cut this. Now, just make it easy on yourself. So kind of after steps 1 and 2, I'm just going to redraw this like this. You can see carbon 3 right here is this carbon right here. I'm just going to make that an aldehyde. So this is 1, 2, and 3. I can draw 6, 5, and 4. That is an aldehyde, right? So 6, 5, and 4. So no one ever said you had to straighten this thing out. Just draw it as conveniently as possible. So then you can see, even though we just produced these nice new aldehydes, well, we're going to reduce them because we have an excess amount of LEH, a great reagent to reduce stuff with. So H- hydrides coming in. We're going to make these both into alcohols. So our final product will look like this. Right? And I can do 1, 2, 3. What was it? 6, 5, 4, just to make sure I end up with the right amount of carbons. Okay? Down here, I'm going to go to races to give myself some room. So we have another alkene, and you can see we have Cl2 and methanol. So this is going to be, we are going to start the addition of of Cl across double bond. However, we're going to stop because we have a large amount of methanol as our solvent, and it's going to participate in the reaction. So first thing is draw your cyclic chloronium ion. Obviously, you need to whisper that under your breath to kind of, use your amazing organic chemistry vocabulary. So I'm going to use, I'm going to just make my chlorine 2 wedges. No reason for that. Could be, and it will be 2 dashes. So we will have a racemic mixture going on here. So if these are 2 wedges rather, our ethyl group will be a dash. So remember, then we bring in methanol, and remember this mimics an epoxide attack in acidic environment. Acid, put that in parentheses. So we're attacking the more substituted carbon. So we'll be attacking right here. Electrons kick off, and the ethyl will flip up to be a wedge. So our final product that we're going to draw before we tack on the plus and antimer is a wedged chlorine up top. Then it's going to be a wedged ethyl down low. And then it's going to be a dashed O-methyl. Okay? And I can draw this a little bit better. I can give it more space over here. So wedged chlorine, that was produced by the leaving group. We have a wedged ethyl. And we have that dashed O-methyl. And like we said, plus an antimer, because we absolutely do produce the other cyclic chloronium ion, and we then have the opposite stereochemistry at both positions. Okay, last but not least, we have a lovely alkyne. And you can see we have H2 and Lindlar, so again, this is going to be a hydrogenation of a triple bond, but we're stopping in the double bond. Which one, you may ask? Well, these are the cis double bond reagents. So just make sure, right, we have 1, 2, 3, 4, 5, 6, so double bond at 3. 1, 2, so this is 3. Double bond, make sure it's cis. 1, 2, 3, 4, 5, 6. As long as you can draw that imaginary dotted line and you don't cross it, you are good to go. That does it for problem 1, gang. On to 2. Okay, gang, in problem 2, we have 4 fill in the reagent questions, okay? So if we take a look right here, so if you almost need to think of, take on a retrosynthetic approach here, that's totally fine. If you can see it from front to, beginning to end, that works great too. So when I take a look at this here, here's what I see. I see in between carbons 2 and 3, right? Because we still have 5 carbons on both sides. I see a double bond, but not only that, a cis double bond. So I know at some point I had to have come through of this alkene. 1, 2, 3, 4, 5. 2 pentine, right? Okay, so that means I have a good leaving group here. I need to do some eliminations to get to a triple bond, right? So the first thing I would do is I would throw in, and again, I need to work in between these carbons right here, so I need to make a Satsef elimination product, not a Hoffman. So very first, right off the bat, I will throw in some NaNH2, and if you want to throw a solvent in there, like DMF, DMSO, acetone, whatever your favorite is, you go for it, why not? So this is just going to be E2. That will create this product right here. Then, right, that's only an alkene, so what we need to do is we kind of need to set ourselves up to do a triple, get that triple elimination, the double elimination rather. So what we can do is across that double bond we just created, we can do something like Br2 and CBr4, or it could be 2 chlorines. Basically, we need to produce, and I'm not going to reflect stereochemistry here, but we need to get 2 good leaving groups to set ourselves up to do a double elimination, right? And we can do that with, again, you guessed it, the base from 1, sodamide, right? We'll do excess, right? To do a double elimination, right? To get us that product that we want. Let me make sure, yep, just that. Oh, and I did put DMF up here. Let me just make sure I'm reflecting everything I did on the exam. Oh, I did CC. This is CBr4. It doesn't matter really. CCl4, whatever. And last but not least, so this, after step 3, that is what gets you to the 2 pentine. And at that point, to take it on home, all you need is Lindlar's and hydrogen, right? H2 gas. So that gets you to that cis double bond. So moving on to the second one. So you can see, I hope, in the product, we have a diol, and they're on the same side, the OHs. So you can see they were added in a syn fashion, and we know one reaction that does that, and that is our osmium tetroxide reaction. So we know that the final step, if you want to think about it, is that OSO4, H2S, and to get that done, we need an alkene. So we need to go through this intermediate right here. Well, let me draw it in the same direction right there. Yep, that alkene right there. So we kind of need to work from here to get to that alkene. So what we can do, and you can see this is a Satsef elimination if we have a good leaving group on this carbon right here. So one thing we can do reliably, since we're starting from nothing, is go back to our roots yet again. We can use our very picky friend, bromine. We can do radical bromination. We know with 100% confidence it's going to go virtually 100% on that tertiary carbon. Then step 2, because we'll have this right here, use your favorite small base. Why not hammer NH2 minus yet again and use your favorite solvent. I think, and here I use DMF. Doesn't matter. HMPA, acetone, DMF, DMSO, it all works. And last but not least, step 3, because that would set us up for this. Then osmium tetroxide gives us the diol across the double bond on the same side of the ring, same side of the molecule, gets you that syn addition. That is the second one. So right here, problem 3. So what's interesting here is we have 1, 2, 3, 4 carbons, 1, 2, 3, 4. So really, we have a triple bond where we're just knocking it down enough to then stick a halide on the end. But it's not just any halide, because if it was bromine, it might make our time a little bit easier, because I'm thinking we work to something like this, and if only we could just do an anti-Markovnikov addition of HCl, but that only works with bromine actually. So what we can do, or what I think we can do, is this. If we get to here, we can do something like this with the hydroboration reaction, right? We can go from here to here, because we know how to step down from this triple bond to that alkene, and then we could then use SOCl2 to do SN2, and here, so I'll write hydroboration, and then I can write SOCl2, and that would get us our product. So I think we have a path forward. So what we can do here is a first step, and I'll just switch to blue. We need to knock this down to a double bond. Use Lindlar's and H2, but if you want, but I'm gonna go ahead and give this a different look just so we use all the reagents here. Elemental sodium, liquid ammonia, that technically, it's the trans reagents to give you a trans double bond, but it doesn't matter because we're terminal here. There's no concept of cis and trans. So now, we've done this. So now we need to do hydroboration. So what we can do is BH3 as a second step. Then as a third step, we need to annoyingly do the big NaOH, hydrogen peroxide, H2O2, and water. That will get us to this product right here. Then last but not least, trusty SOCl2 to get the OH to eventually become a good leaving group in the mechanism. Check the mechanism in the alcohol section if you are interested to know more. And then we then stick on our chlorine and boot off what will be some derivative of OH. That is problem 3. And last but not least, we have this reaction right here where we end up in an epoxide, okay? So how do we do that? What's interesting to note is that here's a tertiary carbon, here's a tertiary carbon, but this tertiary carbon remains unchanged. So we're not doing anything over on this position right here. Only this carbon and this carbon do we work with. So we need to get to, we know our last step is to get something like this and treat it with MCPBA. How do we get to that alkene? Luckily, we already have a good leaving group, and I hope you're already seeing what we need to do. We need to do a Hoffman elimination. So grab your big favorite bulky base, LDA, or potassium terbutoxide, whichever. That will give us that double bond, the Hoffman product, and then we can then toss in MCPBA, taking it home. And that does it for the fill in the reagent section. So on to 3, without ado. Alright gang, in problem 3, we are tasked with drawing the mechanism for this anti-Markovnikov edition of HBr. And if you've watched the anti-Markovnikov edition of HBr video, you know this one has a special place in my heart. So, let's have some fun. So, if we take a look here, not only do we need to draw the mechanism, but at the very end, we need to explain why it's a chain reaction. So, we do need to show initiation steps. So what we will do first is we will show the peroxide bond here. Now again, I'm drawing ROR, but this could very well just be hydrogen peroxide, HOH. Oh boy, that's a whole bunch of mess right there, right? But this is just a generic peroxide. So we will show, for the first time in a long time, homolytic cleavage, right? So what that will be, you can show 2RO, and make sure you illustrate that that is a radical, okay? So after we've produced our, a radical from the homolytic cleavage of the peroxide bond, what we will do then is that one of them, we can just work with one from now on, will run into HBr. This will abstract a hydrogen, and remember, we haven't worked with single-headed arrows in a while, and let me switch to black for the arrows, but one electron reaches out, hydrogen takes one electron and reaches out, that they form bond together, and what that does, that kind of leaves bromine to then just take the other electron in the former HBr bond, and what we get after that is some generic alcohol that we don't care about anymore, but we get the very coveted, what we need to move forward, bromine radical, okay? So now we enter in our organic piece, and we see the magic of the anti-addition, because bromine waltzes on in, bromine radical, it reaches out, it wants to join the party. One of the electrons in this bond right here will go to linking up and forming a carbon-bromine bond. The other electron has to go somewhere, so we have to choose. Do we make a primary radical or the secondary radical? That's not even just a secondary radical, it's a benzylic radical, and of course, we want to form the more stable radical, and we will do that by putting the radical electron right there. So you can see by doing that, I didn't even stick with my using black for arrows, but we then make our bromine bond to the less substituted carbon, and we have our radical electron perched on the carbon where it's happier, okay? So then we need to kind of take care of that radical, get rid of it. So what we do is then we run into yet another HBr. Oh, radical electron right here. So this carbon will reach out and go, all right, hydrogen, let's boogie. I'm taking you. We're gonna make a bond, and that leaves yet another bromine to then be a radical. So, at this point, we have drawn the mechanism. And if you got to this point and you've included this right here, as long as you kind of indicate what this is, you've explained that it is a chain reaction, because by sticking on the bromine and quenching this radical right here, by abstracting that proton, you then produce another bromine radical, and this bromine radical just goes right up over here, gets the party started yet again. So that does it for 3, gang. On to 4. Okay, gang, in problem 4, we have this reaction here where we have an alcohol, we have an alkene, we throw in some acid, right? We're in an acidic environment. Strong acid, H2SO4, it's catalytic, meaning if we start with it at the beginning, we should produce it at the end. Acidic environment. And we get this product over here that looks nothing like the beginning, so what the hell went down? Don't freak out, right? Just go with what you know, little by little, and eventually you'll reach that pinnacle moment where the light bulb goes off, and you go, no, 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 not today. I know how to solve this. So if we take a look here, we're just gonna do what we do best, right? We see a few things here that we can protonate. However, right, I hope one thing that helps if you can spot this off the bat is this is a cyclization reaction. We formed a 6-membered ring, okay? So, in forming that 6-membered ring, who was the attacker? Who was the nucleophilic atom? Well, it was oxygen, okay? So, we want oxygen to kind of be negative, so don't protonate that out of the gate. I know that's something we've done before, but we have this double bond. That's a better candidate, right? Because if we protonate that, we'll produce a carbocation, and that's something the oxygen can attack. So let's start there. And again, if you even did this first, there's no, you might just see, you do it, it takes you somewhere, and it's maybe not the right place. So what we can do is I'm going to go ahead and draw this again. Whoops. Just making stuff up. Okay, so I'm going to draw H2SO4, but I'm just going to kind of expose the protic hydrogen, drawing everything else, right? H2SO4. So the double bond is going to reach out. It's going to pick off that proton. We'll dump electrons onto the oxygen. So in drawing this, do I make my carbocation here or here? Well, let's think about this. Oxygen is in the ring, so I'm going to give that a 1. This is carbon number 2, carbon number 3, carbon number 4, carbon number 5. Damn, even if we put the carbocation here, it's still not going to give us 6. However, hopefully you're sitting at your computer going, Joe, because if we put the carbocation here, look at that. We have a cheeky tertiary carbon sitting right here. So if we put our carbocation, let me draw this correctly, up, over, down. Yep, that's how organic chemistry works in my brain. Plus charge right there, we can then shift with a hydride shift the carbocation to that tertiary carbon. I'm going to draw this down here, and I think you're going to see something very nice and promising. Carbocation here. Let's count again. 1, 2, 3, 4, 5. Bingo, bango, bongo. That is 6 carbons. And remember, neutral oxygen, right? Neutral OH, not an amazing nucleophile, but when you have something as reactive as a carbocation, it can definitely do the job. So what we're going to do, 1 will attack 6 from the back side right there. So we've already numbered it. What I'm going to do is I'm going to mirror my product up here. I'm going to put oxygen at the top. I'm just going to go ahead and draw a ring. Then I'm going to go 1, 2, 3, 4, 5, and 6. So again, we play who is attached to whom. So at 2, we have a methyl group. You can see that's already looking real good for us. Nothing at 3, nothing at 4, nothing at 5. However, at 6, we have a methyl and an ethyl. So methyl, ethyl. I did forget to bring along the hydrogen that this alcohol had at first, because we do have a positive charge, right? We can't just skip that step. This isn't a complete reaction. This is a mechanism, so we want to show all this. But we do have everything. We have the regiochemistry correct. We are structurally hooked up excellently. all we need is to bring back, right, this is catalytics, so catalytic acid, so we have it at the end, we better regenerate it. So we'll bring back the O-, SO3H. It will just pick off that little pesky hydrogen, dump electrons onto that oxygen, getting rid of that positive charge that oxygen is super not a fan of. And looky, 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 we got exactly what we want. Our product up top. So that, I saw this problem a while ago. I really liked it because it's kind of, it doesn't fit in the category of any like reaction. It's kind of like, I would say, a generic mechanism, but it uses everything, a lot of things that we've covered this semester, and you absolutely know how to do it. So that's 4, gang. On to 5. In problem 5, it's all about tautomerization. So if we take a look up here in problem 5, letter A, we need to mechanistically show how this ketone tautomerizes from its keto form to the enol form, okay? So, and again, on the solutions, I have double-headed arrows, so I'm going to be using, reversible, because that's actually what happens. It's an equilibrium. So, first and foremost, you need to protonate your carbonyl oxygen. So I will show this right here. So the oxygen right here is going to grab H+, dump electrons onto the oxygen and hydronium to make it water. So again, I'll show arrows like this. I'm not going to reflect the size of them just because being lazy. However, that then protonates our carbonyl oxygen. We have a plus charge, so we can see there is the ol characteristic of the enol, right? Enol, alkene, ol, alcohol. So we then produce water. What we can do then is, if we use this water, remember, you do this correctly if you start with acid and produce acid at the end. We need these electrons to kick up like this. One method, the way we can actually get them to move up like that is if we expose a hydrogen. We can have water, grab that hydrogen, kind of doing an elimination-esque move. Electrons can swing down, we can form a double bond. So this is how we would get the enol then, double bond. Then we have our OH up there. That is the enol, the keto tautomerizing to its enol form. Okay, so explain why the keto form is more favored than the enol. So you can see we have different bonds in these two structures right here. Namely, the most important trade-off we make going from here to here is, so in this structure we have a carbon-oxygen pi bond. Over here we have a carbon-carbon pi bond. And enthalpically, I'm talking delta H, I'm talking about the strength of these bonds. This is a more stable bond. This is a better bond than this. So the keto form is favored because you have this carbon-oxygen pi bond that is better, the double bond better, than the carbon-carbon pi bond. And that is why the equilibrium heavily favors the keto form. Okay, that does it for 5, gang. On to 6. Okay, gang, for problem 6, we have 3 parts. So in this first part, we need to explain why, when this reaction is performed, there's no optical activity in the product mixture, okay? So we can see we have an alkene. We're going to be doing a Markovnick combination of HCl, and I think this is a old hat for you at this point. We know we're going to protonate this double bond. We're going to form the most stable carbocation. We're going to shift it if necessary, and then we will attack on both sides with that Cl- producing a racemic mixture. So let's just illustrate that mechanistically. So just to even save myself some space, we will protonate the double bond. It will grab H+. So kind of drawing an arrow down here. We have the choice of the tertiary carbocation or the secondary. We are definitely making that tertiary carbocation. The Cl- that we produce, right, it's going to attack that now sp2 trigonal planar carbocation, and it can do so. I'm actually going to move the charge on this side. It can do so from on top or on bottom. And you can see that as we do that, right, this carbon is attached to a methyl group, an ethyl group, and a propyl group. So we definitely are producing a chiral center, a stereocenter. So choose whatever you want to wedge and dash. I'm going to use the chlorine and the methyl group. So we can wedge this methyl, dash the chlorine, and at the same time I will also draw the fact that we can produce, and we will produce, a wedged Cl and a dashed methyl. You can put that they are 50-50. And you can use the beautiful R word, the keyword, the racemic mixture is produced. This is enough to illustrate to someone that you know what you're talking about, and this is why there's no optical activity produced in your mixture because, right, because that we have a racemic mixture, we have equal amounts of the enantiomer. Each one is going to bend the plane of polarized light one way, and the other one's going to bend it completely the exact opposite way, so they cancel each other out. Okay? That's A. Moving on to B. I'm going to do B up here. I'm going to have this room down here for C. So, can a structure have multiple stereocenters but be achiral? Now, if you've done practice exam 2, you already know the answer to this. There was a true-false question about this. The answer is a structure can have multiple stereocenters and be achiral. And remember, you know, part of the problem is show an example. All we need is a plane of symmetry, and that completely destroys something's ability to be chiral. So, if you look at this structure right here, this is absolutely a stereocenter. We're attached to a hydrogen, a bromine, and this group are not the same. And that exactly goes for the same right here. However, you can absolutely see that we have a plane of symmetry. And that means this structure is meso, which means, you know, something needs to be chiral. It has to have a non-superimposable mirror image. The supposed mirror image of this structure would look like this. However, because there's a mirror, because this is meso, because it has a plane of symmetry, if I just flip this over like a pancake, it's the same thing. I can actually flip this over, superimpose it, and it's the exact same structure. So I'm beating the point to death. The answer is yes, you can have a structure with multiple stereocenters, and it can still be achiral as long as you have a plane of symmetry. Okay, last but not least, we need to determine the two relationships, we need to determine the relationship between these molecules. We're going to DTR these molecules, right, between them. So if we take a look here, we're going to assign R and S here first. So the methyl group is our lowest priority group. So the bromine is the highest priority. Second comes the oxygen. Third comes this group over here. So for this carbon right here, we look like we are S, and we actually are S. Over here, I'm going to erase my little priorities. Deuterium is the lowest priority group, so we've got a nice situation here. So this structure is actually, like, this part over here is priority number 1. Ethyl is 2. Methyl is 3. So we look R, and we actually are R. Okay, so R and S. Moving on to the other side. Oh, now we have to double switch, right? And make sure you check. Make sure no one bamboozles you, you know, and doesn't set you up to get, you know, these be structural isomers, right? Make sure the the chiral centers you're looking at are all hooked up, right? Methyl, methyl, OH, OH, bromine, bromine, deuterium, ethyl, ethyl, right? Because I could have totally switched this OH and this deuterium over here, and they would have been structural isomers, right? There wouldn't have been a stereochemical relationship between them. Okay, so we're all hooked up the same way. So bond to bond, you know, the actual atom to atom connections. So if we take a look here, I'm just going to go ahead and draw this over here and just double switch on this new thing over here. So what I'm going to do is methyl is my lowest priority, so I'm going to put that over here. I'll switch these two. So initially I'll have a wedged bromine. I will have a line, planar OH. But what I'm going to go ahead and do is switch the OH and the bromine. That is my double switch. OH, bromine. So I've maintained the same stereochemistry here. So now let me do the same exact thing over here. I'm going to switch the deuterium and the ethyl. Ethyl dash deuterium, lowest priority group facing away. Methyl's just hanging out. Then I'll switch the ethyl and the methyl. Ethyl, methyl. Now I can assign, okay? So these are equivalent, but I'm going to work on this. So you can see priority number 1, priority number 2, priority number 3. So I look R, and I actually am R. That's my stereochemistry on the left. And over here, highest priority is this big group over here, then the ethyl, then the methyl. So I look S, and I actually am S, and looky, 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 I'm opposite at this stereocenter, and I'm opposite at this stereocenter. So to DTR between these molecules, we got a classic pair of enantiomers, left and right hand. Okay, gang, that was problem 6. We got one more. Stick with me. 7. Let's finish strong. to finish out the practice final exam here on jOeCHEM, we have a synthesis problem, gang, and we need to, using 2-butene, as much as as we need to synthesize 3,4,5-trimethylheptan-4-ol. So it's not uncommon in a synthesis problem for someone to not, draw the structures for you on the left, and on the right they might just give you the names. So yet again, naming coming, in clutch. If that's why putting in the effort, and even though it's boring as hell, it's worth it. So obviously 2-butene is not too mind-blowing to, break down. You make sure this is nice and bold. Okay. 3, 4, 5. All right, so heptan. So we have 7 carbons. Let me just draw 7. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5 trimethyl. So 1, 2, 3. 1, 4, 5. There's our 3. And then on 4 as well. 1, 2, 3, 4. We have our alcohol, right? Because we know this 4 corresponds to the ol, which is an alcohol parent in the parent name. Okay, so let's count our carbons, because clearly we have a whole mess of carbons over there, and we are working with 4 in our starting material. So we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That makes sense, because heptan, 7, trimethyl, 3, that makes 10. So we have units of 4. 10 is not divisible by 4. But I hope what you're thinking, maybe, is that we need 2 of these, and that would give us 8. We somehow need to get a piece of 2. Well, that's not a shell-shocking idea, because we could cleave this in half with ozonolysis. That's something we know how to do. So we definitely can use 2 butenes, and then we can cut one in half to get 2 as well. So this is, mathematically, it makes sense. That's why I'm not trying to jump ahead and explain the whole synthesis. I'm just saying in the realm of counting carbons, it does add up. It does make sense. There is a path forward. So we're definitely working. We can see that we want to somehow smush 2 4-carbon pieces together, as well as, we need to make convenient cuts for ourselves. Maybe it's going to be a piece of 2 pieces of 4 that go to 8. Then we smush together a piece of 2, or maybe we have a piece of 4 combining with a piece of 2, and then we link up with another piece of 4. So when we make our cut here, which I'm going to draw downwards, keep that in mind. Make it convenient for yourself. You don't want to screw yourself and make something impossibly difficult. You want to make this as efficient and as easy as possible. That gets you more points, and you keep your sanity. It's a win. It's a classic win-win-win, a triple win. Okay, for my office people. So if we're looking at this, you can see clearly that this is evidence of doing a Grignard reaction. There's no trickery about that whatsoever. So we need to make a cut. And we know this was once a carbonyl carbon. So I hope what you're seeing is 1, 2, 3. And I'm going to try, okay, 1, 2, 3, 4. We do have symmetry here. So if you make a different cut than me, you're not doomed. You just made a different cut. So 1, 2, 3, 4. And 1, 2, 3, 4, 5, 6. Okay, if we make a cut right here, this is a piece of 4, and this is 1, 2, 3, 4, 5, 6. So that does line up. That is this could be one, we can take this directly back to 2-butene, and then we're going to have to do a little extra work for the 6-carbon piece, but that's totally fine. So what I'm going to go ahead and do is I'm going to draw a line like this. We will need acidic workup to get to the Grignard product, but I know my Grignard carbon needs to be right here. So it needs to be an interior carbon, it doesn't matter which one. So I'll do MgBr. And then down here, I need 1, 2, 3, 4, 5 carbons. And it's on here 1, 2, 3, 4, and 5. It's on carbon 2 that I have a carbonyl, a ketone, and then it's on carbon 3 that I have a methyl group. Okay? Cool. So what I'm going to do is I'm going to just make this happen real fast because it's super easy to do. So we can take this back. I can just do magnesium. You can choose to make it elemental and add THF. As long as there's magnesium over that arrow, you're looking pretty, looking good. We can get that from doing bromine. And I think you know how to make this happen nice and easily. We can just do HBr. Markovnikov addition, super easy, right? It's going to go on one of these 2 carbons. They're equivalent. We already have most of this, part of this problem done. Now we just need to figure out how we get this 6 carbon piece and link this back to 2-butene. So what I'm hoping you're seeing is if we step this back, right, this is a ketone, but clearly we had to oxidize this up. We could use something like PCC. We have an OH. Okay, now does not this look like a Grignard product? It does. So let's make a convenient cut for ourselves. I hope you're seeing 2 carbons right here. Let me just make sure yep, this is exactly what I'm doing. Okay, cool. I can make a cut right here. 4 carbons yet again. And here's the super nice part. Once I step this back, again, we will need acidic workup. We will need this 2-carbon aldehyde. And we will need, look at that, a secondary Grignard. Why not just MGBR? And you don't even have to do anything with this because you've already made this. We already made this up here. So this can basically just, you can show, okay, I already made this. I'm just grabbing more of it. It's totally fine. So we just need to see how this works. And look at that. I think we know how to do this in one step. Because if we do ozone, I always forget these reagents. Yep, the methylene chloride, CH2Cl2. A second step of, I can never remember this. There's obviously zinc and then the acetic acid, right? You cleave at the double bond, right down the middle. You make aldehydes, that's an aldehyde. Gang, thank you for rocking with me. If you're watching this, that means you're taking a final soon. Good fucking luck. Like in a, not in a bad way, like a very encouraging, positive way. You got this. If you're watching this video, that means you probably watched a lot of videos on this website. That means you've done a lot of problems and you've logged a lot of work. You got this. Trust yourself, believe in yourself, get plenty of sleep, drink water, take a deep breath, and crush this thing. Believe in yourself. And if you're watching this also, thank you for supporting jOeCHEM and using jOeCHEM. But you're a rock star. You got this. Take that final. Enjoy winter break. Hopefully I'll see you for OChem 2 in the spring or the fall. Good luck. You got this.